Previously, we discussed divergence operator as well as gradient operator for unstructured grids, such as the case of an MPass grid, which is shown here. Previously, in a paper, A Unified Approach to Energy Conservation and Potential Vorticity Dynamics for Arbitrary Structured C Grids, the equations for numerically solving divergence, gradient, as well as curl were shown in this way. That's in a previous video, so please check that. But I also wanted to include another version, which I found on UXArray, which doesn't necessarily apply to this type of unstructured grid, but at least a software UXArray, which is a software on Python for calculating, basically dealing with unstructured grid data and calculating gradients and things. They have a gradient operator, which they apply, which is slightly different, but you can kind of see maybe a better, more general way of explaining this. So we have a cell, and this is our center cell, and we can do this for each of these cells. We just need to look at what's around them. But this cell is a 2D image here, and that's okay if you're using a 2D grid, but most grids are 3D, so the center cell looks like this. So you can imagine it's going down underneath. So we want to find the gradient at this point. So what we need to do is we need to sum up all of these kind of gradients that cross between two center points. So this is a uniform hexagonal grid, for example. The difference for this kind of grid as it's written, though, is that the gradients are applied across edges, while here they're this is a little bit different. The grid is a different shape, and the gradients are going through here. I personally like this better because you want to imagine that the gradient is going through this face, which is like a face here. But they're basically equivalent. This one is better for if you want to calculate, if you want to run a numerical model to make predictions, but this kind of thing is okay if you're just doing data. So between each point, we have a few things to define. One, at each of these, we have this normal arrow. So we define it like N12 is the normal arrow directly in the center between the two edges of the face. So this line. L12 is that distance between them. And the volume of C star, for example, the center one, is actually going to be the literal geometric volume, whatever the volume of this is. If it was a square, it would just be, L cubed. But here it's going to be a little bit different. You have to use some more complex geometric equations to do that. But the way that we do it is to find the gradient at a point. We first, later we divide by that volume, but what we're basically using this volume to normalize, the thing that we're normalizing is the sum of all of these kind of like derivatives. Because a gradient is kind of like a combination of those different dimensions, but the gradient, we're essentially solving for a kind of gradient of flow that comes through each part of this. In a normal grid, it's it's kind of like in each direction you have a gradient, and then you have the y gradient, and each of these have a bunch of arrows. But here we're kind of summing up a bunch of, not gradient, but you have a thing here, you have things flowing in two different separate directions. But here we don't really have an x and y direction, so we're just going to sum up all of the flow that's coming in these edges, which is in the red dashed lines. And so for face F, we use this notation partial C star, which is basically each of these differences across the edges. We look at each of those faces. For the face, we take the value, and these points, this point is in the center of this volume. There's also a point here and a point here. So C2 and C1 are actually kind of on this edge here, and then the distance L12 is between them. So what we do is we take the value, we call phi is the value, the gradient that we're trying to solve for here. Take the value of that here plus the value of here divided by 2, which puts it right here, smack dab in the middle. That's what this does. It's the value of phi in the middle here. And then we need to normalize by how long this point is taking up, because the point is supposed to represent taking up this whole line here. So that's why we normalize or multiply by Lij. And then we also need to multiply by Nij to show the direction of the flow. If the values here is like 2 and 1, we're subtracting the 2, we're going to do 2 minus 1, or sorry, maybe 1 minus 2. If the normal is supposed to represent, like, it really doesn't matter just as long as n is consistent everywhere, like it's pointing out everywhere, or it could even be that this one points out, this one points in. It's just to make sure that our signs are consistent so that the flow is going in the correct direction, so it adds up to the total gradient in the correct way. And so we just need Nij. So what is Nij? It's a number. It's either 1 or it's -1, that kind of thing. Maybe you can say it's 1 if it's pointing out, -1 is pointing in, that kind of thing, just as long as you're consistent. So we could technically make them all pointing out, and we could say that they're all, I believe we can just say that they're all, 1 in that case. So that's a little bit more complicated. I'm not exactly sure how to define that for this, but you can see, for example, in this direction, in this example, you have n going out and going in, and they have either value 1 or -1. So that's all for this video. As for the other videos, you can check I guess it's like the kind of forum, or basically I send messages on the YouTube channel in one of those tabs. You can check there, but basically to summarize, I won't be back for a while, but I do have plans on what to do in the future, so you can check that there if you're looking forward to it. And also feel free to leave any comments or that of any kind of material you'd like to see. It doesn't matter how simple or how complex, I can make a separate playlist for that. All right, thanks.